And now it also gives me the pleasure to introduce the next speaker and also the final speaker of the session, Una Trivanovic. She is also a PhD student from Switzerland, from ETH Zurich. She's from mechanical engineering and will be talking on some science on combustion. So Una, the floor is yours.
Great, thank you very much for the kind introduction. So as you just said, I'll be talking about my work using enclosed spray combustion of jet fuel as a surrogate for aircraft emissions. So we'll be staying on the topic of climate change and nanoparticles. So when you think about aircraft emissions, chances are what you think about is carbon dioxide. And of course, this is an important component of the emissions. However, it's not the only thing that comes out of an aircraft exhaust. Another thing that's very abundant is water, actually, and the focus of my research, these soot nanoparticles. And a few things happen in this case. For starters, the soot can actually act as a nucleus for the water to condense, and this is what forms contrails. In addition, the soot can act as a direct absorber of sunlight and thus warm the atmosphere in this way. So it's important that we understand what these particles are and how they interact. This is so important, in fact, that these non-CO2 radiative forcing effects account for nearly 2/3 of the net radiative forcing for aircrafts, highlighting the importance of understanding these effects, not just measuring the CO2. On the other hand, these particles can also have a negative effect on our health. So when they're emitted around airports, in particular, aircraft emissions tend to be very small compared to, for example, the particles from a diesel engine, and these have an outsized negative effect on human health. So it's important that we understand what we're emitting. So to understand a little bit more about what these particles are, here I have a small cartoon of what this looks like. It's this irregular particle. They're based on carbon, and we have these primary particles that make up the larger aggregate. Within that, there's also a nanostructure to these primary particles, and we learned about graphene earlier in the day. You can think about this as layers of graphene surrounding a more disordered core in the middle. And what this looks like will really influence how it is able to absorb light and what its direct radiative forcing will be. In addition, we need some way to measure the size of the whole particle. Because it's irregular, we can't attribute a direct measure of the diameter to it, so what we do is we use equivalent diameters, and what's often used in the field is the mobility diameter, so the size of a sphere with an equivalent electrical mobility. Next, we want to quantify in some way the chemistry of the particles, and for this we often use the organic carbon to total carbon ratio, and you can think about this as the organic carbon are the volatile or semi-volatile compounds that are condensed on the surface, and the total carbon is everything including the solid parts that we have. Finally, one thing that's very important but actually very rarely measured in the field of aerosol science is the specific surface area. This often isn't measured because it's very difficult to get a large enough quantity of particles to do what we call nitrogen absorption, but it's very important because it's one of the most important metrics for quantifying the toxicity of any kind of nanoparticle, including soot. And so in my work, what we've been doing is we've taken real jet fuel that you would use in an airplane, we've turned it into a spray, and we combust it in a quartz glass tube, which allows us to carefully control the conditions within the tube. And we can also change the conditions through what we call the effective equivalence ratio, which is just a measure of how much fuel and oxygen there is in the mixture, with 1 being stoichiometric conditions and greater than 1 meaning you have excess fuel. And so by doing this, we're able to produce particles which have the same parameters, which I've just pointed out, the primary particle diameter, these OCTC ratio, in the laboratory as we do in real aircrafts. So now to understand how these particles grow in a very simple flame, here we have a premixed flame. So first we start off with what we call inception. This is where the particles go from the gas phase into the first solid components, and these are just a few nanometers in diameter. As they continue to travel through the flame, They go from a few nanometers to a few tens of nanometers through surface growth, where chemical reactions with the surface grow the particles. We can also have aggregation, where if two come together, they chemically bond together to form these necked dimers. Then, as we continue farther, we get agglomeration. During agglomeration, the particles simply by chance collide into each other, and they form a weak point contact bond. And at this point, they can grow considerably to as much as hundreds of nanometers in diameter. And in the final phase, we might have oxidation. This is the only phase where the particles actually decrease in size rather than continuing to increase in size. And so this is because of excess oxygen surrounding the flame becoming entrained, and then it oxidizes away to either a smaller size or completely into carbon dioxide. So this is a very simplified model, but in reality, in aircrafts, in engines, we have a much more complex turbulent flame, and so this is what we researched. So in our complex flame, we took a sampling probe and inserted it at different heights above the burner, which is analogous to the residence time that it's experienced in the flame. And so this let us measure how it's evolving. So here we see that as we increase the height above the burner, the mobility diameter increases steadily throughout the flame. And because it's never decreasing, this suggests that we have minimal or no oxidation. Then we looked at the primary particle diameter, and we saw that this actually did not change from the smallest height above the burner that we investigated, 5 centimeters. It stayed about constant throughout the flame. So to understand why this happened, we also did some computer simulations. And first, we see in the blue line here that our simulations matched excellently with the data. And similarly, with the primary particle diameter, it was in good agreement with our experimental data. So what do these experiments show us? The simulations say that in this range where we were not able to measure experimentally, we actually had single primary particles that are significantly growing through surface growth. And so as they grow in size, they reach a point at about 5 centimeters where we have these aggregates of just a few primary particles. From here, agglomeration takes over as the primary mechanism, and they continue to grow into these large mobility diameters, but the primary particle size stayed roughly the same. Next, we wanted to understand something about the nanostructure within those primary particles, and we did this using Raman spectroscopy. So first, to put this into context, we have Raman spectroscopy from graphene, which again we talked about today. So graphene is a very ordered crystalline structure compared to the soot. And here we have the D band, which you can think about as the amount of disorder in the system. The G band, which you can think about as quantifying how graphitic or ordered the structure is. And also the 2D band, which we won't focus on so much. It's more a function of how many layers of graphene there are. If we now go to the few layer graphene, we see a very small D band and a large G band. So this suggests that we have a very ordered structure. When we go already just to graphene oxide, where we have more defects in the system, this D band significantly increases, and we can use this D to G ratio to quantify approximately how disordered it is, and we go from 0.06 up to 0.9. And also in the literature, we have these carbon black nanoparticles, which are quite similar to soot, and they're actually a commercial nanoparticle, which is in car tires. In our work, we saw this characteristic D to G peak, and at the lowest height above the burner that we investigated, we had a D to G ratio of about 0.8. And as we go through the flame to higher equivalence ratios at 10 and 25 centimeters, we see that this is increased a little bit. And at the exit, when it exits the reactor, it goes up to 0.9. So this suggests that the particles are actually becoming more disordered as they travel through the flame. And so this could be because of reactions on the surface. And importantly, when we compare this now to real aircraft soot from the literature with this dotted line and the shaded area representing the different conditions that an aircraft can operate at, we see that we're able to reproduce quite well the nanostructure that we see in the Raman spectroscopy between real aircraft soot and our own laboratory soot. So up to this point, I've just shown you for a single equivalence ratio or a single combustion condition what the results look like. So here is that same one that we've seen, the same spectra you saw in the last slide, and the distribution of primary particle sizes, because it's not just one. But we can also change the combustion conditions. So if we increase slightly the equivalence ratio, we see virtually no change in the Raman and the primary particle size distributions. If we continue, however, to equivalence ratios of 1.73 or even 1.88, now we see a significant shift in the primary particle sizes. So these leanest conditions here are similar to aircrafts, while something like the 1.88 with a 23 nanometer primary particle size compared to 13.6 nanometers, this is more like what you might find in a diesel engine. Now, interestingly, across this same range, we see that the D to G ratio, or the amount of disorder in the particles, has decreased significantly. This means that the larger primary particles tend to have a more ordered nanostructure. And if we compare this directly with the median primary particle diameter, we see that we have an excellent correlation between these two. And this is important because this determines how it interacts with sunlight, and it could be that these more aircraft-like particles do not absorb as much sunlight as the more diesel-like particles, for example. And other work has actually shown in a completely different flame, they disaggregated the particles based on their size, and they saw the same trend. So this suggests that this really is a function of the size of the particles and not just the different conditions that we used in the flame. So now we want to understand also how the changing conditions affect the mobility diameter. So I'll point out that these 2 points are the lowest points we saw in the last slide, and we actually looked at some even smaller equivalence ratios here. So by increasing the equivalence ratio, we were able to dramatically increase the mobility diameter from this extreme case of an equivalence ratio of 1.29. We had an mobility diameter of about 15 nanometers, and we increased it by about an order of magnitude to 160 nanometers at this highest equivalence ratio. Interestingly, in this range, we saw a very constant primary particle diameter. And so this is interesting because we've grown the mobility diameter, but not the primary particle diameter, which only started to grow off the end of this graph when we increased the equivalence ratio to 1.7 or higher. And so this is important because what it tells us is that the mobility diameter increased because we had a higher rate of nucleation, so more particles with the opportunity to run into each other through agglomeration, but surface growth was not acting importantly in this range. And so here we have some images of the particles, and you can see that they're quite similar. And importantly, the range that we're in here of about 14 nanometers falls squarely in the range of aircraft soot. So now the last thing, and the most important thing that we wanted to look at, was this specific surface area. So we used nitrogen absorption to measure this, which also allowed us to look at the pore size distributions. So at the lowest equivalence ratio we showed here, we had a specific surface area of about 160, and looking at the pore size distributions, we see a relatively small number of pores, which at the small pore widths begins to increase. As we increase the equivalence ratio a little bit, we see basically the same trend in the pore size distribution, but we have a slightly higher number of pores, which of course results in a higher specific surface area. If we go to even higher equivalence ratios of 1.46 or 1.59, now we do not see the same trend anymore. We have an increase in particles in the range of 2 to 4 nanometers. And this is important because now we have a significantly higher specific surface area, and this higher specific surface area can in turn lead to higher toxicity of the particles. And we want to understand what caused these pores. So one thing that could explain this is the difference in temperature. The closer we get to stoichiometric conditions, the higher the temperature will be in the flame. And what happens at high temperatures is that oxidation, if any is occurring, occurs quite fast, and carbon is removed quickly from the surface of the particles. At slightly lower temperatures, oxygen is able to diffuse farther into the particle and remove carbon from the inside. And this could explain why we have this porosity forming at the higher equivalence ratios compared to the lower equivalence ratios. And I'll point out that in our work, this higher equivalence ratio of about 1.59 matched very well with aircrafts at takeoff, or what we call 100% thrust. So this could indicate that we would see the same phenomenon in aircrafts at these conditions. So now to summarize what I've told you, what we did was we took a spray combustion of real jet fuel, and we used this to recreate aircraft like soot in the laboratory, allowing us to get a better understanding of this in a laboratory setting. Thanks to this device, we were able to measure the specific surface area of soot and also recognize that there are these internal pores that are contributing to the surface area. And finally, we also observed that as the primary particle increases, we also had an increase in the order in the nanostructure, which will affect, in the end, the interaction of light of these particles. So with that, I want to thank you for listening and welcome any questions.
Thank you, Una. Now we have a short Q&A session moderated by Dr. Yen.
All right, now it's time for Q&A again. Yes, please.
Hello, good afternoon. Thank you for your interesting talk. I'm just interested when you mentioned about the flame turbulence. Can you expound on that? Did you consider the air turbulence around the flame? Because let's say during the takeoff, there should be an air turbulence around the combustion region, which should affect the formation of the soot, or let's say the air turbulence could affect could result to disintegration of bigger particles. Yeah, if you just consider that air turbulence, if you already mentioned about the flame turbulence, and if you compare, let's say, the standard Reynolds number of the flow regime around the furnace, which you recreate in the laboratory setting. Thank you.
Yes. Can you hear me? Yes. So, of course, the turbulence is very important, and the reason I brought this up is because a lot of the fundamental research on how these grow is done in these laminar premixed flames, which are in a lot of ways an oversimplification of the real system, as you said. Our system is also very turbulent. We haven't measured exactly the Reynolds number, and there are quite a few other differences compared to a real aircraft, of course, so it won't be one-to-one, but both systems will have turbulence, and I think the important thing about the turbulence is that it will give you heterogeneous nanoparticles, so you don't have just one. This is why we also had the distribution of primary particle sizes, for example, rather than one single primary particle size, because they're forming in different regions of the flame, so we really have to talk about the distribution of particles as opposed to just one. And so when we're comparing to the literature on aircrafts, we're comparing to the whole distribution of particles, not just one single particle.
Thank you.
All right. Any other question? Actually, there are questions. There's one question from the online audience. Let me read it out. What numerical model equations was used for considering the chemical reaction, fluid flow, and also particle tracking?
Yes, so we used a model called discrete element modeling. And so what this does is basically we have the particles from after they've become those solid particles in the inception phase, and we track how they undergo surface growth and agglomeration through the flame. In this model, we do not account for the fluid flow. We just look at how the particles are moving through random chance through a small space, and then extrapolate this through to get average quantities for the particles. And when we run this several times, we can see how the distribution would occur, because each time it's a stochastic model, and so it's not exactly the same each time.
All right. Any further question? Perhaps, oh, yes, good.
So also, thank you for your presentation. I also understand this is probably then continued research, but you were also talking about, for example, toxicity, and I think your results, I guess, give way to certain actionable measures that we could implement, for example, at takeoff and so on. So do you think that from these results you could give some actionable advice to how, for example, flight traffic is executed?
Yeah, of course, it's a very complicated system. I guess there are a few easy things that you can do. One is avoiding idle in aircrafts, in airports, which would improve the number of particles that are accumulating just unnecessarily. There are some things that you can do using alternative fuels. Some fuels tend to produce fewer particles than others, but it's important in this case to look at the trade-off because, of course, particles are not the only pollutant. It's just one of them. But some newer fuels do tend to produce fewer particles, so you can remove it this way. I've also seen some ideas around spraying water vapor, essentially, at the exhaust to try to remove the particles from the local air. And another very important thing that I hope can come out of this research is we still need to understand more about what causes contrails to form in some areas and not others. And so there is work being done out there using the characteristics that we're able to gather about what the particles are to put it into models, which will then help us to understand why in some cases we have contrails and some we don't, and maybe we could modify flight paths to avoid contrail heavy regions.
Very interesting. Thank you.
Okay.
So
Yes.
I wanted to ask, in your Raman spectra, when you have the graphene versus the graphene oxide, and then you again heat up even more, in that case, there is two things happening. One is the structure is changing. As from graphene, you go to graphene oxide. The other thing is it is also getting aggregated, right? So you have a heterogeneity in your system. So then how do you structurally assign the Raman spectra? Is it because of the basic structural change, or is it coming from the heterogeneity or aggregation?
So in the example that I gave, it was not pure graphene. It would have been few layer graphene and an aggregate of it. So there was still that small D peak. It wasn't a perfectly crystalline structure because I guess it was a graphene that was made with methods that were not super precise. And so in all the cases, yes, it's a heterogeneous measure of an average of what you're seeing. And typically also when we do these measurements, we'll measure at several different points in the powder so that we understand how it's varying from position to position. So it's not as precise as it would be in a purely crystal, like if you're looking at a single crystal, but it still gives us some idea when we are comparing spectra within similar materials how it varies.
All right. If there's no more question, please allow me to ask a few. Number one, actually, it follows what the last audience has asked. You're following the carbon formation, and you mentioned a number of parameters that affects carbon formation. I wonder, what is the relationship between the chemical structure of the fuel? We can have normal jet fuel, but now people are also talking about the biojet fuel and other types of jet fuel. When the chemical structure of these fuel change, how does that affect carbon formation?
Yes, this is very important, and this is something that's an active area of research in the field right now. So one important thing is traditional jet fuels tend to have a high aromatic content in the fuel compared to some of the biojet fuels which have less of it. So these aromatic compounds in the hydrocarbons that are being combusted, those tend to be precursors for soot. And so fuels that eliminate that tend to have fewer soot emissions, but not all biofuels that are being looked at have fewer soot emissions. So it really is important to look at them individually to make sure that you're really reducing that with the biojet fuel, because sometimes they're not optimizing for that.
Okay, thank you very much. My final question is general. I asked the first speaker about present in PhD. I want to ask you into the future. After PhD graduation, what are you expecting the most, and what worries you the most?
I guess there are a lot of unknowns, so it's easy to answer that what worries me the most are simply the unknowns. But I'm excited about the opportunity to have some more freedom to decide in my own directions. And one thing that I've really enjoyed in my PhD at ETH, where I have the opportunity to supervise bachelor's and master's theses. And this is something I really, really enjoyed. And I think that in the future, I really look forward to having the opportunity to continue working with other scientists and coming up with projects and working on things, with people above and below me, I guess.
Okay, thank you very much. Now there's no more further question. Please join me to thank Una one more time. Now let me hand over the MC.
Thank you, Dr. Yen.